Yeah, good morning all. Hope I am audible. Yeah, today we'll start with module 3. Module 3, that is gate level modeling, right? Yeah, is the screen visible?
Yes, sir.
Yeah, fine. So we'll start with gate level modeling. I can say there are three types of modeling or three types of descriptions. So first basic level of modeling is, I can say it's a gate level modeling. Means whatever the circuits we are analyzing or explaining, right, we'll be doing that with respect to the gate levels or with respect to some logic gates, right? So at gate level, the circuit is described in terms of gates. Example, your AND gate, NAND gate, XOR and all, right? Hardware level, at this level is intuitive for a user with a basic knowledge of digital logic design, right? Okay. So gate types. So in this logic circuit can be designed by the use of logic gates. Getting any logic circuit can be designed by the use of logic gates. What do you mean by logic circuit? Anyone? What do you mean by logic circuit? It has to take some decision. Correct, right? So then you can call it as a logic uh, circuit, right? So Verilog supports basic logic gates as predefined primitives. These primitives are instantiated like modules, except that they are predefined in Verilog. So what we are doing is these gates we can instantiate in the Verilog code, right? So here, so there are two classes of basic gates. So first set is AND OR gates, second set is buffer NOT gates. So clear? What do you mean by gate level modeling? So gate level modeling is a type of modeling, right, or designing where exactly we are concentrating on the basic gates. So how these gates are connected, right? How many signals, right? How many signals are available with respect to gates and all, right? So clear? So basically there are two classes of basic gates. So first one is, or first set is AND/OR gates. So this is one set of basic gates. So second set of basic gates is buffer/NOT gates. You remember this. So in gate level modeling, right, we are describing or we are explaining the circuit with respect to with respect to basic gates. And in Verilog code, we are concentrating on two types of basic gates. So first basic gate is AND/OR gate. Second set is buffer/NOT gate. Okay. So first we'll check AND slash OR gates, right? So AND slash OR gates have one scalar output and multiple. What is this? Do you want to change the color scheme to improve the performance? So here, so in case of AND slash OR gate, so you can have a multiple scalar inputs. I hope you are knowing this. You can have multiple scalar inputs, but you have only a single scalar output. That you can, I think that you have studied in AND or OR gates. So the first terminal in the list of gate terminal is an output, and the other terminals are inputs. So just check this sentence. So in these gates, what we are doing is the first terminal in the list, right? So in the list, whatever the first terminal you can see, that you can make it as output, and the remaining terminals are considered as inputs, right? The output of a gate is evaluated as soon as one of the inputs changes. Correct, right? The output will change depending on the change in the inputs, right? So here, so we are checking AND slash OR gates. So in this AND slash OR gates, you can have a list here: AND gate, NAND gate, OR gate, NOR gate, XOR and XNOR. So these are the type of gates available in AND slash OR gates, right? So here, so this is the logic diagram for the basic gates. So this you can read it as a 2 input AND gate, right, where I1 and I2 are inputs and out is the output. Again, this is 2 input NAND gate, I1 and I2 are inputs and out is the output. See, what you can conclude by looking into these logic diagrams is, in all the gates the inputs are means inputs we are taking as I1, I2 if it is 2 input AND gate. If it is 3 input AND gates, means we can take inputs as I1, I2 and I3, right? And in all these gates, one thing you can observe is output is considered as OUT, out. Clear? This is with respect to 2 input AND gate, NAND, OR, NOR, XOR and XNOR, right? So these gates are instantiated to build the logic circuits in the Verilog. I think this you are knowing. See, one thing you need to understand is while instantiating these gates, right, we need to mention their particular instances or names. Okay, just we'll check this example how exactly you can instantiate AND slash OR gates, right? So in this, out is connected to output port and IN1 and IN2 are connected to I1 and I2. So we'll check this with respect to one example here. So say gates with more than 2 inputs are instantiated by simply adding more input ports. Means if you want 3 input AND gate, means you need to add one more input port. Say it is I3, right? Verilog automatically instantiates the appropriate gate. Means what we are doing is we are checking here how exactly you can instantiate or create any of the logic gates, right? So here, example 5/1, gate instantiation of AND slash OR gates. See, as you know, there are 2 types of basic gates with respect to your Verilog code. One is AND slash OR gate, second one is buffer slash NOT gate. So first we'll check AND slash OR gate, right? So wire out IN1, IN2. See, as we have mentioned here, so first we need to show the output here. We need to show the output, then 2 inputs. So here, how many gates he is showing here? Means in the circuit diagram, right, he wants to use these many gates. Getting my point? Say you have one circuit diagram or say logic circuit where you need to use AND gate, NAND gate, OR gate, NOR gate, XOR and XNOR. Means you need to create these gates or instantiate these basic gates. So how exactly you can do that? Assume that all these gates are of 2 inputs. Am I correct? All these gates are of 2 inputs. IN1, IN2 out. This is with respect to AND A1. This is with respect to AND A1. A1 is say it's a instance or name of the particular AND gate, right? Then second gate is NAND gate. What is the name? NA1. See again he is mentioning output first. Out IN1, IN2. Then OR gate R1. See instead of OR1 you can give any name or 111, right? That is the instance name. Again he is showing out first followed by IN1, IN2. Clear? Next here. More than 2 inputs, say 3 input NAND gate. If it is 3 input NAND gate means, so first you need to highlight the keyword. That means you want to use NAND gate. And what is the instance name or NAND gate name? He is showing it as NA1 underscore 3 INP. So it's a 3 input NAND gate. So first you need to mention output, that is out, followed by IN1, IN2, IN3. Right? Check these two comment lines. So this part is clear, right? More than 2 inputs means 3 input NAND gate means. So first out, then IN1, IN2, IN3. Now see here, gate instantiation without instance name means even you can skip the instance name. What do you mean by instance name? In this example you have named it as NA1 underscore 3 INP. So this part you can skip. You can show only type of the gate followed by number of inputs and output. So in this case I can say it is 2 input AND gate. But here you can see that instance name is missing. Even though instance name is missing, you can call it as legal type of instantiation or legal gate instantiation. Up to this clear? Any doubts here? Any doubts here? Any doubts? Any doubts?
No, sir.
Clear, right? So understood? See, when you can create the particular gates depending on your circuit requirement. Say you are realizing one half adder. So half adder means how many inputs and outputs you can expect? 2 inputs and 2 outputs. Correct? Then what is the expression for sum and carry? What is the expression for sum and carry in your half adder? Anyone? Anyone? Half adder. How you can show the outputs in your half adder? First, sum equal to first Daneshwari. Sum equal to
A bar B plus A B bar.
Means A XOR B. Correct, right?
Yes, sir.
Yeah. So if you are designing a half adder means you can show sum as A XOR B, means A bar B plus A B bar. Means how many XOR gates or what kind of XOR gate you can instantiate? 2 input XOR gate. Am I correct? Correct, right? 2 input XOR gate you can create like this. Then what about expression for carry? Carry equal to A dot B. means you require two input AND gate, means you can create like this. Clear? That is the meaning of gate instantiation of AND/OR gates, right? So this is the this is the truth table for AND/OR gate. See, is it visible? Is it visible?
Yes, sir.
Yeah, fine. So here, so check only this AND truth table. This is AND truth table. This is NAND or NOR, right? So first we check AND truth table. So here, so check this row is I1. Say this is first input. I2 is the second input, right? So I2 we are showing row wise, I1 we are showing column wise, right? Getting or not? When you can expect AND output as high? When you can expect AND output as high? When you can expect two input AND gate output as high? First, if both the inputs are high, correct, right? Then you can expect the high output. Am I correct? Yes or no? Getting or not? Is it correct? Chaya, is it correct? So here, so this is AND gate truth table. At I1, I am showing all the possible inputs. So 0, 1, X and Z. Same way, at I2 also I am showing the same thing. 0, 1, X and Z. So first we will start with I2. So here, 0, 0. When inputs are 0 and 0, output is 0. Getting? When inputs are 0, 1, again output is 0. When it is 0 and don't care, again it is 0. When it is 0 with high impedance, again it is 0. Getting my point? Getting? So next is 1, 0. 1, 0 means 0. 1, 1 means 1. You just check this part. When inputs are 1 and 1, you can expect the 1 output. Correct? 1 with X, again it is X. 1 with Z, again it is X. So X with 0, X with 0, 0. Then X with 1, again it is X. X with X, X. X with Z, X. Then Z 0, 0. Z1 X, ZX X, ZZ X. You need to remember these truth tables. See, you know 0, 0, 0, 1, 1, 0, 1, 1. So out of 4 cases, your output will be high for the last iteration. Correct? That is this one. 1, 1, output is 1. Similarly, you can check the truth table for NAND gate. Getting or not? I hope it is clear. Similarly, you can check one more OR gate. When you can expect OR output as high, out of 2 or out of 2 inputs, if any of the input is high, then output will become high. So here 0, 0, 0, 0, 1, here 1, 1, 0, 1, 1, 1, 1. Correct? Then what extra you can observe is with respect to high impedance, and don't care, right? Up to this clear? Any doubts? Clear? Fine. So this is about your AND slash OR gate. So next type of gate is buffer slash NOT gate. So what happens is, in case of your buffer circuit, whatever the input you are giving, the same will appear at the output side. Correct? Means your output will follow the input. This here. Buffer slash NOT gates have one scalar input and one or more scalar outputs. So remember this. See, in case of your AND slash OR gates, you have multiple scalar inputs and a single scalar output. But in case of your buffer slash NOT gates, have one scalar input. These have only one scalar input and you can expect one or more scalar outputs, right? The last terminal in the port list is connected to the input. Output terminals, or sorry, other terminals are connected to outputs. So we'll check with respect to an example here. So basically I can say two basic buffer slash NOT gates are, one is BUF, one more is NOT, right? Next we'll check the symbol. I think this you must be knowing. So this is the diagram for your buffer circuit, right? So whatever the input you are giving, the same will appear at output, right? The NOT gate, whatever the input you are giving, that will be complemented at the output side. Then how exactly you can instantiate these buffer slash NOT gates, we'll check with respect to an example here. Okay, so basic gate instantiations, check these two. See, while declaring the gates, make sure that first you are assigning the output followed by input. So here BUF means it will show the or it will create an gate. What kind of gate it is? Buffer. What is the instance name? B1, and output is out1, input name is in. Similarly, what about NOT gate? NOT N1. N1 is name of your NOT gate. Then output is out1, input is IN. So if buffer is of say 3 inputs, sorry, in case of buffer you will have only a single input and you can expect multiple outputs, so that you can check here more than 2 outputs. If it is more than 2 outputs, means you can show it as out1, out2 and in, right? So here next is gate instantiation without instance name. So without instance name means you can skip the name of the gate, right? So not out1 in means you are not showing the name of the gate, right? Again, truth tables for so here the truth tables for these gates are very simple. Truth tables for gates with one input and one output are shown in the table 5.2. So what is telling? Truth table for the gates with one input and one output. So you can check buffer gate with how many inputs and outputs? One input and one output. Then again NOT gate with one input and one output. So what you can observe is, in case of your buffer, for the first 2 iterations, right, what will happen? If you are giving 0 as input, means you can expect same 0 at the output, right? Input is 1 means output will also be 1, right? Then if it is x means output is x. If it is z means output is x. These two first 2 rows, I think you are comfortable. Then remaining last 2 iterations, right? Just check. Then similarly, not gate input and output. See, if you are giving 0 at the input means you can expect 1 at the output. If input is 1 means output is 0. Then x means x, z means x. So this is the truth table for one input and one output, buffer as well as NOT gate. Getting? Up to this clear? Any doubts here? So next is buff if slash not if. This is one more set of gates. See, these buff if slash not if, this will again come under buff slash not gates. Means we are still into second class of gates, right? Gates with an additional control signal on buff and not gates are also available, right? See, this if means I can say this is the, so this if is the control signal, right? That control signal will affect your output. Means I can say in other words, your output is dependent on two things. In case of your buff if slash not if, output is dependent on, first is input, second one is control signal, that we will see now. Up to this followed? Up to this, any doubts? Any doubts you can ask. Any doubts? If you have any doubts, so let me know. Yeah. So next one is yeah, we'll just check in detail. Buff if slash not if, right? So if I can say this is the control signal which will affect your output. So I can say control signal, it can have two values. This control signal, that is if here, it can hold two values, or at a time it can hold either 0 or 1, right? So buff if 1, buff if 0, not if 1, not if 0. In buff if 1 I can say control signal is control signal is if, right? And what is the value that it is holding? Its value is 1 here. In case of buff if 0, the control signal value is 0. In case of not if 1, what is the signal value? 1. In not if 0, its value is 0, right? These gates are these gates propagate only if their control signal is asserted. Getting my point? These gates will propagate only if their control signal is asserted. They propagate Z if their control signal is de-asserted. Getting my point? Symbols, we'll check in this diagram or in this figure 5.3. See, buff if 1. See, buff if 1 means it is the buffer. How many inputs? One input, one output. And what is the control signal? Control signal value is 1. Getting my point? Then not if 1. So this is not gate, in, out. And we are showing one more control signal and its value is 1. Now see here, buff if 0 and not if 0. Can you compare first two logic diagrams with last two diagrams? See, in buff if 0, you can compare buff if 1 with buff if 0. In buff if 0, I can say again it's one input and one output. But the thing is, control signal, what is the control signal value? It is 0 here. So we are showing one bubble. Getting my point? Same goes with your not if 0. So in not if 0, what is the control signal? Control signal is if and its value is 0. Got the difference? Got the difference between buff if 1 and buff if 0? In buff if 1, control signal value is 1. In buff if 0, control signal value is 0. Means in case of your buffer, your buff if 1 will propagate only if the control signal value is 1. In buff if 0, it will propagate only if its control signal value is 0. Right. So next is in case of your not if 1, it will give you the output only if the control signal is 1. In not if 0, it will give you the output only if the control signal is 0. Clear? Then these are the truth tables for buff ifs or not if gates, right? So so this is the truth table for buff if 1. Getting? So buff if 1 and control. So input side, I can show how many 0, 1, x, z. Then at the control side, I need to show the same inputs 0, 1, x and z. Right? See, we are checking buff if 1. Correct? So we are checking buff if 1 means if the control signal is 1, then whatever the input you are giving, getting or not? If control signal is 1, then whatever the input you are giving, that will appear at the output side. So assume these are inputs. Here, check this. This is in how many inputs? 0, 1, x, z. Then how many control signals? 0, 1, x, z. And remaining these things, these z, 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 0, 1, x, x, these are all outputs. Getting here? So say, so in case of your buff if 1, so if control signal is 1, then whatever the input you are giving, that will appear at the output side. So you can check the second column straight away. So in the second column, correct, so this is first column, this is second column, this is third, this is fourth. These 4 are inputs, these 4 are control signal. You can check the control as 1. Check this. Can you see this? See, in this case, control is 1. So what happens if control is 1? Whatever the input you are giving, that will appear at output. So check here. Check the second column. Input is 0. Control is 1. So same input you are going to get, because we are into buff if 1. Getting 0. Control is 1. The same input will appear at the output side. Second iteration, input is 1. Again control is 1. The same input will appear at the output side. Then if input is x, means the same x will appear. But if the input is z, means you are going to get x at the output side. Getting? And if control is 0, check the first column. If control is 0, input is 0, then you are going to get z. Then if input is 1, means z. If it is x, means z. If it is z, means it is z. When you can expect these outputs at the first column? If the control signal is 0. If control signal is 1, means whatever the input you are giving, the same will you will going to get. Then this is x, this is z. Same goes with your buff if 0. So what is the difference between the truth table of buff if 1 and buff if 0? In this case, it will check the control signal as 0. If it is 0, means the same input will appear at the output side. Clear? Then same goes with not if 1 and not if 0. Getting? Any doubts here? You can check all 4 truth tables. You can take 2 minutes, right? You can take 2 minutes, go through all the 4 truth tables. If you have any doubts, let me know. Just go through all 4. Go through all 4 truth tables. So this is buff if 1, right? Buff if 1 means control is 1. If control is 1, input and output both will remain same. In buff if 0, control is 0, right? Then if control is 0, inputs and output they will remain same. In not if 1, right? In not if 1, what is the control signal? Control signal is 1, right? Check the second column. Check the second column. If input is 0, then it will be complemented. If input is 1, it's complemented provided control is high. Then what about not if 0? Here control is 0. Check the first column. If input is 0, output is 1. If input is 1, output is 0 provided control is made as 0. You need to remember these truth tables. These are very important, right? You can take 2 minutes, check for all the combinations. Okay, clear? Any doubts here? Any doubts? Okay, we'll stop at this point, right? And next class we'll check the same with respect to some examples, right? Yeah, thank you.